Hi, this is a video lecture about addition reactions to alkynes. Some of these we've already gone over in class, but I'm going to make a complete video of all of the addition reactions that we need to know. The first addition reaction that we're going to talk about here is hydrogenation. We've already seen this with alkenes, and we learned before that if you take an alkene and add hydrogen in the presence of a metal catalyst, you add hydrogen across the double bond, and so you turn an alkene into an alkane. And we also learned that this happened in a syn fashion, which means that both of the hydrogens add to the same face of the double bond. We're going to learn now an analogous reaction for alkynes, and we'll see that the same sort of things happen. And we're going to learn three different conditions that you can use. So in the first condition, we're going to use exactly the same metal catalyst in the presence of hydrogen. This reaction will also give you an alkane. So essentially you can do exactly the same thing, only in this case with the alkyne, you're taking the alkyne all the way down to an alkane. You're still adding the hydrogens in a syn fashion, but you're doing this twice. So you're actually adding two equivalents. So I could put a 2 in front of that hydrogen. You're actually adding two equivalents of hydrogen across that triple bond to give you a single bond. In this particular set of reagents, when you're just using a regular metal catalyst, the intermediate here is actually a cis alkene. So if we could stop the reaction halfway, you might get something that looks like this. And then to go the rest of the way, you would just add one more molecule of H2. The thing is, the reaction can't be stopped at the cis alkane, so you can't stop the reaction to make a cis alkane with these reagents. So if you want to make an alkyne into an alkane, you simply use the same reagents that you would use to convert an alkene to an alkane. Now, what if you wanted to take an alkyne or triple bond and make it into a double bond? You can actually do that, but you can't use these reagents. You have to use a different set of reagents. There's actually two different sets of reagents that you can use depending on whether you want a cis alkene or a trans alkene. So let's look at those individually. To make a cis alkene from an alkyne, you just add hydrogen again to that alkyne, but this time instead of just a regular metal catalyst, you use something called a poisoned catalyst. And the most common one is Lindlar's poisoned palladium catalyst. So if you want to just put Lindlar's catalyst over the arrow, that's sufficient, or poisoned catalyst. But what a poisoned catalyst is it's just a catalyst that's not quite as efficient or reactive as a regular catalyst. And so basically, this allows you to stop the reaction at the cis alkene. It's still a syn addition, and the mechanism would look very similar to what you're used to for any hydrogenation reaction. I just want to give you a few details about Lindlar's poisoned palladium catalyst. So Lindlar's catalyst is simply palladium poisoned with calcium carbonate, lead acetate, and quinoline. And these things make the palladium catalyst less reactive. What this means is that it will only hydrogenate alkynes. Alkynes are more reactive than alkenes, so don't try to use this catalyst to take an alkene to Don't try to use this catalyst to take an alkene to an alkane, like we've learned before in the very beginning of the semester. That was one of our first reactions. So it only hydrogenates alkynes and it does not react with alkenes. So with Lindlar's catalyst and hydrogen, you can take an alkyne and you can make an alkene that has a cis configuration, or it's a cis isomer of an alkene. If you want to make a trans alkene, you can use a different set of reagents. And in this set of reagents, you actually don't add H2 at all. You add sodium metal, so this is sodium with a 0 charge, and that indicates that it's solid sodium metal, and you add ammonia, or NH3, and these reagents will give you the trans alkene. Both of the hydrogens on this molecule come from the ammonia, and this is another one of our special radical mechanisms. So I'm just going to cover this reaction mechanism very briefly, and I'm going to show you why this set of reagents will give you a trans alkene rather than a cis alkene. The first step in this reaction is for sodium to react with ammonia. When you put sodium metal in ammonia, the sodium actually dissolves. So you take the sodium metal and it actually dissolves and it gives you sodium ions plus basically free electrons. So this is just a free electron, and basically just using the ammonia as the solvent here. So the sodium now is a sodium ion. It's soluble in liquids, and the electron here is going to go on and react with one of those alkynes. So here the electron itself will directly attack the alkyne, and it reacts with the pi bond in the alkyne. So what we get here is this interesting anionic radical species. So the carbon with the radical is sp hybridized, and that radical is in a p orbital. And then the carbon with the anion on it is actually sp2 hybridized because its lone pair of electrons is in a hybridized orbital. And then there's that last p orbital, which I'll draw kind of in and out of the plane of the paper here, which is making the pi bond, right? So it's making that pi bond. Okay, so the next thing that happens is this anionic carbon is going to attack ammonia to get rid of its anion, and it produces a negative charge on nitrogen, which is a really strong base. And this carbon is still sp2 hybridized, and it's now a trigonal planar carbon. But there's still a p orbital here with that contains the radical. This thing here, the radical can actually go kind of back and forth between the top face and the bottom face of this p orbital. So you really have, you can think of this as of a species where the radical is kind of on the top of this p orbital, and it goes back and forth, or it can fluctuate down to the bottom as well. The next step for this reaction is for another electron from ammonia, so from this first reaction that we saw up here, another electron that's dissolved in the solution attacks this radical species, and it does so to form the most stable product, and the most stable product is from the electron adding to this particular version of the radical. And that is so that this carbon, when it rehybridizes, the two R groups end up being in the trans configuration. And that's more stable than the alternative possibility where the two R groups are cis to each other. And so this is where your trans stereochemistry of your product comes from these particular reagents. The last step here is simply for another equivalent of ammonia to lose its hydrogen to this carbanion. And these hydrogens have both come from ammonia. So now we've seen 3 ways that you can hydrogenate alkynes to either make alkenes that are cis or trans, or to make an alkane. So now I'm going to move on to hydration. And just like before, a hydration is adding water, but this time we're adding it to an alkyne. Now, when we talked about hydration of alkenes, there were 3 ways we did it. If you don't remember them, go back in your notes right now, pause this video, go back in your notes, and check out what they were. So the first one we talked about for alkenes was an acid-catalyzed hydration, and it was kind of the reverse of an SN1 mechanism. The acid-catalyzed hydration does not work for alkynes, so don't use those reagents for alkynes. When we hydrate alkynes, we are actually going to form carbonyl compounds rather than alcohols, and I'll show you why in a moment. It's important to understand that the regular acid-catalyzed hydration does not work for alkynes. It works for alkenes, but it does not work for alkynes. So if you just add sulfuric acid or phosphoric acid in water, this will not work for alkynes. So alkynes are a little bit different than alkenes in that way. Let's look at one way to hydrate alkynes. The first set of reagents I'm going to talk about is adding mercuric sulfates in the presence of H2SO4 and water. This essentially has the same effect as just adding sulfuric acid and water to an alkene, but here you're doing it to an alkyne, so you need this mercuric sulfate. Now, as you would expect, you would get an alcohol, or you get OH added to one carbon and a hydrogen added to the other carbon, and this is not a stereospecific reaction, so I could draw the hydrogen up or down, it doesn't matter. But you get Markovnikov addition here. Now, the reaction doesn't stop here, because when you have an alcohol directly attached to an alkene carbon, this will rearrange. It does something called tautomerization. It will essentially just rearrange so that the carbon that right now has the alcohol on it will end up with a double bond to that oxygen. And the hydrogen, that extra hydrogen, will actually end up on the other carbon of the double bond. These two different molecules are called tautomers. On this side, we have something called an enol. So the ene comes from the alkene part, and the ol comes from the fact that it's an alcohol. So this is an alcohol attached to an alkene, and it's called an enol. And this is the keto form because it's a ketone. So this is often referred to as keto-enol tautomerization. So I want to talk a little bit more about tautomerization. And you can see here from this general reaction I've written, which is a tautomerization, it's really just basically a movement of one of these hydrogens that's on the carbon adjacent to the carbonyl. So this is kind of, it's actually called the alpha carbon. So this is the carbonyl carbon, and this is the alpha carbon. So this is a hydrogen attached to the alpha carbon, and it essentially is eliminated, and then you could think of it as the same hydrogen going to that oxygen instead. And so you basically, if I wanted to draw electron movement arrows, I would draw them like this. Now, tautomerization can be catalyzed by acids or bases. I'm going to draw out the acid-catalyzed mechanism. So if I have acid in solution, it's usually in the form of H3O+, And here I have a Lewis base and a Lewis acid, which can exchange a proton. Now this oxygen is electron deficient, and in order to satisfy the positive charge in the oxygen, this bond can break, and it can pull the electrons from this hydrogen-carbon bond with it. At the same time, this hydrogen falls off, and we can write it as if it's being accepted by another solvent molecule. So this is the mechanism going from the keto to the enol. And notice that the hydrogen that ends up on the alcohol does not necessarily have to be the same hydrogen that was attached to the molecule in the first place. Let's go back the other way. So starting from the enol, to get to the keto form, when you have acid in solution, the alkene here acts as a Lewis base to become protonated. And this will give you a carbocation, and the carbocation prefers to be in the the carbon attached to the oxygen, because there's a resonance structure here. And to satisfy that positive charge, the hydrogen will just pop right off, and it can be accepted by a molecule of the solvent. And so we've gone from our enol form to our keto form. And really all of these steps are in equilibrium. So it depends on the structure of the ketone and the enol that you're dealing with, but in most cases, the keto form is more stable. And so in the reaction that we just talked about above, when we form the enol, it pretty much immediately just tautomerizes into the keto form. And so the product of hydration of alkynes is a ketone or some other analogous carbonyl compound that results from the initial formation of an enol. All right, so now let's add HX or acid halides to alkynes. Recall that we can do this for alkenes, and we've learned about this. In this reaction, the alkene acts as a nucleophile. It attacks the hydrogen of the hydrogen halide. Your more stable carbocation will always form faster, and then as long as there's no rearrangement that's going to happen, the next step is for the halide to attack the carbocation and give you your alkyl halide product. This always follows Markovnikov's rule, and we see the same sort of reaction for alkynes. The product depends on how much of the acid halide you add. If you add one equivalent, you can just simply add one equivalent and stop it there. So to add an acid halide across the triple bond in a Markovnikov fashion, all you have to do is add HX, and X and H end up being trans to each other. You can also add two equivalents, and if you do this, you will completely eliminate the pi bonds here, and your halogens will both be attached to the Markovnikov, or they both add in a Markovnikov way, so they'll both be attached to the more substituted carbon. Now, the mechanism of addition of HX to alkynes is not exactly the same as the addition of HX to alkenes, and you might see why if you just look at the first step. If this was an analogous mechanism to the alkene addition, we would basically expect a carbocation to form here. And this is a carbocation on an sp2 carbon, and this cannot exist. These are much, much too unstable. Remember, that was kind of one of the rules we talked about, is that you don't have carbocations on sp2 hybridized carbons. So because we get the Markovnikov product in both cases, and because we observe that the halogen is always trans to the hydrogen, there's a different mechanism. And in this mechanism, there's basically two equivalents of HX that are reacting at once. So as your triple bond attacks the hydrogen of one equivalent of HX, the halogen of another equivalent is attacking the more substituted carbon from the opposite face. And so in this one concerted step, you get the trans addition of H and X. And then in the next step, if you're adding two equivalents of HX, the next one can just be written as if it was an addition of HX to an alkene. So this is your normal mechanism that you know well. Now the intermediate carbocation here actually has a resonance structure, which makes it a little bit more stable. And the product here is called a geminal dihalide. Geminal just means that both of the halogens are on the same carbon. There's also a way to form anti-Markovnikov geminal dihalides so that both of the halogens add to the less substituted carbon. And recall, so we saw that there was this way that for alkenes before, and then we also know for alkenes you can add HBr in an anti-Markovnikov fashion if you add hydrogen peroxide. So now we're going to talk about an anti-Markovnikov way to add HX to alkynes. You can also stop this reaction halfway to just get the one addition of HBr if you'd like, but you just have to add one equivalent of HBr. And this reaction, just like the alkene reaction, only works with HBr. All right, now there's the addition of X2. Remember that we did this with alkenes, so we took an alkene and we added X2 like a Br2 or Cl2. We got a 1,2 dihalide, which means that the two halogens were connected to the carbons one carbon away from each other. And this always happens in anti-addition. So I didn't show that well, I'll erase this. When we do this same sort of thing with alkynes, we also get the addition of X2 across the triple bond, and we can stop at one equivalent if we'd like. So if we add just one equivalent of X2, so Br2 or Cl2, we will get this sort of a product. So again, we're getting anti-addition, and those halogens will be trans from each other. And if we start with an alkyne and add X2 or two equivalents of X2, we will get this. And in this case, so like let's say this is my first equivalent and my second equivalent here and here. Those halogens all add anti to each other. Okay, so I'd like to stop here for a moment, and I'd like you to try number 1 on your lecture review. Now let's talk about ozonolysis of alkynes. But first let's remember what we know about ozonolysis of alkenes. If you don't remember this reaction, please review your notes before you go on. Ozonolysis of alkenes cleaves the alkene double bond and replaces the carbon-carbon double bond with a carbon-oxygen double bond. In this reaction, the first step is to add ozone, and the second step is to use a reductive workup. The reductive workup can either be water and zinc, or it can be a dialkyl sulfide. The product is either ketones or aldehydes, depending on what's attached to the original carbons. When we perform ozonolysis on alkynes, we use similar reagents. First, you add ozone, and in a second step, you simply add water. with ozonolysis of alkynes, we're simply cleaving this carbon-carbon triple bond, and we're going to replace the 3 carbon-carbon bonds with new bonds between carbon and oxygen. So in your product, you will now have 3 bonds between carbon and oxygen. You'll have a double bond to one oxygen and a single bond to another, and this results in carboxylic acids as the product of ozonolysis of alkynes. Now I'd like you to try number 2 on your lecture review.